Today we are dealing with a two-way slab. What is two-way slab? When the length to width ratio of a slab panel is less than or even equal to 2, such type of slab is called as a two-way slab. Length of the slab panel is denoted by Ly and the width of the panel is denoted by Lx. Clause number as already mentioned, see page number 90 of IS code 456/2000. Now as per the code, because the maximum bending moment is in the middle portion of the slab, so it is to be divided into two strips, edge strips and the middle strips. The width of the edge strip, this is the width of the edge strip. If this is Lx, longer span is Ly, shorter span is Lx, then width strip, the edge strip, we can call it the edge strip, is Lx by 8 on this side, Lx by 8 on this side, that is 3/4 of Lx is the middle strip. Similarly, when we are talking about the edge strip on this side also, it is Ly by 8, Ly by 8 is the width, and rest of the portion is the middle strip. Whatever we are designing, it is for the middle strip in the shorter direction as well as this direction also. Now we are calculating the bending moments, and the maximum bending moment, I have already told you, it is in the middle strip in x direction as well as in y direction. Now we can call as x direction, we call it mx. If in limit state, we can call as mux. Alpha x into w into Lx square, and my, that is in the direction, we can call as alpha y w into Lx square. W into Lx square remain constant. Value of these two constants, alpha x and alpha y, can be calculated from table number 26 and 27. Table number 27 is only used when the slabs are simply supported. Otherwise, in all other cases, we have to use table number 26. Now, there are various types of cases which have been dealt over here in the IS code. There are 9 cases dealt for different types of two-way slabs. Let us deal with this. All 8 or 9 cases which has been explained over here. Case 1. Interior panel. Interior panel means this is the suppose main panel. There is one panel on this side, one slab is on this side, other slab. So on all the 4 sides, when the slab is there, we call as the interior panel. Means the main reinforcement is not only here, but it also provided in the continuous edge also. This is we call as an case number 1, that is interior panel. Case number 2, when one shorter edge is discontinuous, one is the shorter edge, and all other 3 edges slab is continuing for the other panels, in which the reinforcement is terminated over here in this direction, but it will continue in this direction also, in continue in this direction, in continue this direction. That's why these reinforcement directions are also shown on there. Third, case number 3, when longer edge is discontinuous. When longer edge, the other 3 edges are continuous. So all the 3 slabs on all the 3 sides only except on the longer side, that is Ly, when longer edge is discontinuous. Next, 2 adjacent edges discontinuous, 2 adjacent edges continuous. Here there is discontinuity of the reinforcement at these 2 edges and continuity of the reinforcement at these 2 edges. Now, 2 shorter edges discontinuous, means for the longer edges there is a continuity of the slabs panels and there is no slab on this side. Second condition, then the 2 longer edges are discontinuous, or we can say two shorter edges are continuous, longer edges are discontinuous. Here the reinforcement is terminated over here, and continuity of the reinforcement in this panel also, in this panel along the main panel itself. Now there are two more conditions that I have dealt in this page. On this page is, first, case number 7, one longer edge is continuous, means other three edges are discontinuous. Here you have seen at the continuous edge the reinforcement is to be provided, means you will find some moment over here at this continuous edge, and accordingly in table number 26 you will find the sum coefficient along this edge also. Case number 8, when one shorter edge continuous and all other three edges are discontinuous. Here this continuous edge has got the reinforcement, and other three edges will be reinforcement will be discontinued over here. Now the last case we can call this as the ninth case, which is nothing but all the edges are discontinuous. Means reinforcement is not going in this direction, not coming in this direction. All the four edges, this is the case number 9. This is the case number 9 that we are dealing so far. And now, here in this video, we are dealing with a design of a two-way slab for case number 9, when all the four edges are discontinuous. All the four edges are discontinuous. We are starting with a room size, that the panel size is 2.5 cross 3.5 meter. That is Ly, or we can call L by B, Ly by Lx. Ly is 3.5 and Lx is 2.5. Code says that as the ratio of L by B, that is L by B, the longer dimension upon the shorter dimension, if less than or even equal to 2, we call it as a two-way slab. Less than or even equal to less than 2. Even here should be equal to is also there, no doubt. But if it is greater than 2, that will be a one-way slab only. It has already mentioned clause number D1111, page number 19 of IS code 456 2000. Now, first of all, we start with the depth of the slab. How much depth we should consider? For the depth of the slab, span by 20 into modification factor. And that modification factor already given for clause number 24.1.2 into page number 39, that is span by 35 into 0.8. When it is a simple one panel, it is taken as 35. If it would have been a continuous panel, right, already mentioned in other 2 to 8 cases, at that stage instead of 35, you will have to take this as a 40. This comes out to be, say, 35, this comes out to be rounded on the higher side, say 100. Considering overall depth as 120 and effective depth as 100. Now the load calculations. While making the load calculations, as usual, we have to go for the dead load, live load, floor finish. Dead load 2.5 into 1 will always be the width of the slab, which is 1000 mm, that is 1 meter. This is the overall depth of the slab. Dead load, live load, floor finish is only taken as 0.5 to 1. And when you add all the loads so far, it comes out to be 6.0 kilonewton per meter. The design load will be multiplied by 1.5, that is WD, 9.0 kilonewton per meter. Now considering case number 9 and substituting value for alpha x and alpha y for the Wx, Wd into Lx square, One thing, whatever type of calculation that we are seeing, we are calculating, this part will remain constant. Only the value of alpha x and alpha y will be changed. Now from table number 26, we can go for case number 9. Alpha x comes out to be 0.138 and it comes out to be this much. Alpha x and alpha y can be calculated, and we are taking the maximum values, and we are getting the maximum bending moment that can be calculated. From this, first of all, we will calculate the value of alpha x and alpha y, but r is equal to 0.138 FCK, that is 2.76, as we are considering M20 FE415. Now, from table number 26, where I already told you that we are using the table number 27 only when we are using a simply supported slab. After interpolation, we can find out the value of alpha x and alpha y for a ratio of 1.4. For a ratio of 1.4. Substituting value of alpha x, WD and LX will remain same. The maximum bending moment comes of 4.78 and 3.15 kilonewton meter. Rounding it on the other side, 10 and 8 kilonewton meter. Now, D required MUX upon R into B, as we have seen in the last page, it is 2.76 into B will always taken as 1000. B will be always taken as 1000 for a slab. So D required comes out to be 60.19. We have already taken as 100 mm. So D required is less than D provided. So we can say our design is safe. Now we can find out the value of area of steel in the shorter direction, that is for MUX, and longer direction we call MUY. So AST in X direction and AST in Y direction. Using the empirical formula, the value comes out to be 295 and 232. Rounding out on the higher side, say I call it 300 mm square, and this is 250 mm square. Now, using a 12 mm bar diameter, I am just calculating the center to center spacing, comes out to be 376.6 mm center to center, making it as 300 mm center to center. Now we have to apply the check also. And this is always provided on the shorter span. Now whether we have to see whether this is adequate or not. So we have to see for the maximum spacing, it should always be taken that it should not be greater than 3D or 300 mm, whichever is less. And 3D means when D is 100, that is 300, and 3D is 300. So we are providing, say, 300 mm center to center. So it is adequate. So our spacing is right. Similarly, we have provided the spacing is 376, making it 300. Actual spacing is whichever is less. So now as per the IS code, which is less. So actual area of seal provided will be, spacing is 300 instead of 376. Instead of 370, I reduce it to 300 and we will find out the actual area of steel we have provided. It comes down to 376.66 mm square, which is greater than the required one. So we can say our design is safe. Similarly, we can find out the area of steel in the y direction for that ASDY, and that will also be the same as 300 mm center to center. Now we have to apply the checks. When we apply the checks, first of all check for shear. WD, LE. LE here comes out to be nothing but it is LX. WD LX by 2. It is 11.25 kilonewton. Tau VU upon BD, it comes out to be this much, 0.112 Newton per mm square. PT 100 ASD upon BD, ASD means 376. B will be 3000, D will be effective, is 100.76. From this PT, as per code, table number 19, page 73, and interpolation, the value for tau c can be calculated 0.56, and k times tau c should be greater than tau v. Value of k as per the code for page number 72 is 1.3 up to 150 mm. So 1.3 into 5.6 should be greater than this. So we can say our check for shear is okay. We need not to provide any shear reinforcement so far. Now we go for next check, that is check for deflection. Modification factor time deflection ratio. Modification factor time deflection ratio. As per the page number 38, the modification factor can be calculated as per figure number 4. Curve will be 240 curve. Because 0.58 of 415 comes out to 40. Modification factor comes out to be 1.4. That is 35 we have already taken into span by actual depth ratio. So 49 is greater than 25. For deflection it is safe. Now with the last check, the check for LD, that is development length. 1.3 times m1 upon v plus L0 should be greater than LD. LD will be given as over here. Tau BD is to increase by 16%. So it comes out to be 1.92. Substituting the value, we are getting the value of LD as 564.14 mm. And substituting the value for m1 v upon L0. L0 is nothing but 12 times bar diameter or 12 times bar diameter or effective D, whichever is greater. Our effective D is 100 and we are using the 12 times bar diameter, so 144. That's why this L0 is taken as 144. And if we solve it, we are getting this value is not, it is 1300 mm. Actually, it's coming out to be 1299.5. So we can call this as 1300 mm, which is greater than 564.14 mm. So we can say that our design for all the three checks, check for shear, check for deflection, check for LD, is safe. As I already told you, L0 12 times bar diameter down, whichever is greater. And our diameter is already known, 12 mm, 12, 12, 144, that's why it is 144. That's over and all. Thank you very much. Thank you very much.